This is Shane Picard bringing you another geometry video. Today we'll talk about proportions in triangles. Really, this lesson is just an extension of some of the prior lessons we've already looked at. The first rule we'll look at is called the side splitter theorem. Before we do so, let's just take a look at this example problem. As the two triangles below are similar, find the value of x. So these are the two triangles. We have one smaller triangle and one larger triangle. We're trying to find the value of x here. In a couple ways we can do that. First of all, we might compare the sides of the smaller triangle to the sides of the large triangle. So for instance, 30 is compared to 45. So 30 is to 45. As the length of this small side, we need to figure that out. It's 84 minus x. And the longer side is 84. So there we go. This, you can see, reduces down to 2/3. We end up with 2/3 equals 84 minus x over 84. So we'll cross multiply. 3 times 84 minus x is equal to 2 times 84. We need to divide both sides by 3. We end up with 84 minus x is equal to 2 times 84 minus divided by 3. 84 divided by 3, that's 28. And 28 times 2 is 56. Now we need to add x to both sides. And we'll subtract 56 while we're at it. So we end up with x on the right is equal to 84 minus 56. That's 28. X equals 28. So we were able to find x by establishing a proportionality in here. What we're going to do now with the side splitter theorem is begin to pay attention to this situation that arises when we have a line inside, or a line segment inside the triangle, which is parallel to one of the sides. Side splitter theorem says if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. What that means is that instead of comparing the triangles, we can begin to compare the actual segments. Let's take a look at that. In this particular instance, we know that x is 28. We also know that this segment here must be 84 minus 28, which is 56. So the question for us then is, how do these segments compare? How does 30 compare to 15 and 56 to 28? Let's just take a look. 30 over 15 is equal to 2. And 56 over 28 is equal to 2. So we can see that these segments are proportional. In other words, we don't need to compare the sides of the triangles. We don't need to deal with this 84 necessarily. We can see that there's a proportionality between the segments themselves. That's true anytime we have a triangle and a segment which intersects two of the sides is parallel to the third side. So for instance, if this were 6 and this were 5 and this were 3, we can find this value by simply comparing the sides. 3, we'll call that x. 3 is to 6 as x is to 5. And we can cross multiply. This is 15 equals 6x. Divide by 6. X equals 2.5. So again, we were able to find x without taking the time to really think about the triangles involved. The next rule we need to look at is essentially an extension of the side splitter theorem, something we call a corollary generally. This is called, of course, a corollary to the side splitter theorem. It says if three parallel lines intersect two transversals, then the segments intercepted on the transversals are proportional. In other words, we can take another step away from the idea of the triangles. So for instance, suppose we have a triangle like this, and we have multiple parallel lines that intersect the sides of this triangle. We really don't even need to have this portion here. We can begin, if these lines are parallel, we can begin to compare just the segments themselves. We don't even need the whole triangle. as long as we can establish that these lines are parallel, we can be sure that all of these segments are proportional. The reason for that, of course, is when you look at the side splitter theorem, it says these segments, we'll call these A, B, C, and D, E. It says that AB is to BC as AD is to DE. There's a proportionality that's set up there. If we were to continue these sides a little bit further with another parallel line, well then in this instance, the new segments CF and EG would also be proportional to these segments back here. And so you can see that the proportionality can be extended indefinitely. And once you begin to establish this proportionality, it turns out you really don't need the top of this triangle or any of these segments. A comparison at any of the segments created by these parallel lines will suffice. As an example, we have a situation in which we have 3 parallel lines. We have 2 transversals. And so we can be sure that the value of A is to B as C is to D. That is, A is to B as C is to D. There's a proportionality that's set up in there. Here's a problem that maybe we could exercise this particular corollary on. It says some sailmakers use a computer to create a pattern for a sail. After they cut out the panels of the sail, they sew them together to form the sail. It asks us then to find X and Y. How do we find them? Well, we set up a proportion. Here we can compare 2 to X and 1.7 to 1.7. So 2 is to X as 1.7 is to 1.7. I think you can see pretty quickly that this is equal to 1. So this must be equal to 1, which means X must equal 2. So that was pretty straightforward. And then if we move down here, we can see that 3 is to 2 as Y is to 1.7. And so we can cross multiply. 2Y equals 3 times 1.7. So we multiply 3 times 1.7, and it looks like that would be 5.1. 2y equals 5.1, divide by 2, divide by 2, and y equals, looks like it's 2.55. I think that's correct. Maybe something we should check, and of course that's in feet. So we can use this corollary to find values when we have parallel lines which intersect the sides of triangles. Last rule we need to talk about, which applies inside of a triangle, is called the Triangle-Angle-Bisector Theorem. It says that if we've got a triangle, and we have an angle bisector in the triangle, then the opposite side, that's this side down here, we'll call that side AB. AB is divided into 2 segments which are proportional to the other 2 sides of the triangle. Let's label this point of intersection D. What it says is that AC is to AD as CB is to BD. So there's a proportionality that's set up there as well. Let's put some numbers on this and see if we can actually come to some conclusions. Suppose this is 12 and this is 8. And let's further suppose that this segment DB here is 6 units. Could we find the value of AD? Very simply, we put 12 over AD and set that equal to 8 over 6. In this case, 8 over 6 reduces to 4/3. And so we have 3 times 12, which is 36, equals 4 times AD, and therefore AD equals 9. So we can use this rule to find segments when we have an angle bisector in a triangle. Those are the additional rules you need to know about proportionality within triangles. I suggest you do a few problems on your own, and as always, if you have any questions, please send me an email.